Hello. My relatively ambitious goal in this project is to describe and explain what an adiabatic process is for an ideal gas, and then to derive the pressure-volume equation that is shown right here, and in addition be able to show that it will plot nicely on a pressure-volume plot. And finally, and almost as an afterthought, to integrate this PV equation and show how to find work. An adiabatic process is one in which there is no heat that is exchanged with the surroundings. Here I've shown a piston. This particular piston is well insulated. That's one of the two options really for normal adiabatic processes. That means that no heat comes in and no heat goes out. The other way to simulate or approximate an adiabatic process is to very quickly move the piston up or down so that the process changes its pressure and volume, and then of course its temperature, so quickly that there isn't time for heat to flow in or out of the system. So let's get started on the derivation. The first thing that we can note is if no heat can go in or out of the system, then dq will equal to 0. Now, that should mean to you that if no heat goes in and out of the system, if dq is equal to 0, then the heat that's in the system remains, and therefore, if we change the conditions, that it is likely, it is almost mandatory, that the temperature is going to change. The heat stays at 0, but the temperature changes. All right, dW for an ideal gas is equal to minus P dV, and P is equal to RT over V. We use a molar V. So dW must be equal to minus RT over V dV. From the first law, we know that du is equal to the derivative of heat plus the derivative of work, and therefore du has to be equal to 0 minus RT over nu dV, which means, of course, that du is equal to minus RT over V dV. And here, of course, we're using U to represent internal energy. Because it's an ideal gas, let's just write this out. Because we're using an ideal gas, du is also equal to CV dt. Therefore, CV dt is equal to minus RT over V dV. And we can divide both sides by t, so we'll get CV dt over t is equal to minus R dV over V. Now, I can integrate this expression by simply drawing integral signs on both sides. On the left, we're going to integrate from t1 to t2, and on the right, we're going to integrate from v1 to v2. This is an integral you recognize. CV is a constant. It's going to come outside, so we're going to have 1 over t dt. Same over here. The r is a constant that's going to come outside. We're going to have minus r, and then 1 over v dv. So this particular integral then will become CV log of t2 over t1. If you have trouble with this particular integration, you need to go back and review integration for logarithms. And you might need to review logarithms in general unless your math is fairly solid in that area. So then we're going to have minus r times the log of v2 over v1. And you will note that I can simply switch this sign and get plus r times the log of v1 over v2. Now the next thing I'm going to do is divide through this term here and this term over here by CV. So I will have the log of t2 over t1 equal to r over CV times the log of v1 over v2. The next thing I'm going to do is to raise this to a power. All right, I'm going to raise this to a power and move this term up into the exponent, sort of at the same time. This was t2, t1. We're going to probably need that. So we have t2 over t1 is equal to v1 over v2, parentheses, raised to the power of r over CV. Raised to the power of r over CV. All right, step 4 had a few moving parts, but step 5 is not going to be that complicated. In a previous video, we showed that the gas constant was equal to the heat capacity at constant pressure minus the heat capacity at constant volume. So we're going to replace that r right there. So we will get T2 over T1 is going to be equal to V1 over V2. And you'll note that if we simply replace the r with Cp minus Cv, the first piece will be Cp over Cv. And then the second piece would be Cv over Cv, so that'll be simply minus 1. So that becomes that exponent. In step 6, we're going to let a new variable, we're going to name gamma, equal to the ratio of the heat capacities, the heat capacity at constant pressure over the heat capacity at constant volume. And then we're simply going to substitute that in. So now we'll have T2 over T1 is equal to, it's going to be V1 over V2. And this will be a little easier to write. Now it's going to be just gamma minus 1. Great. We set out to find an equation about pressure and volume, and now we've developed an equation about temperature and volume, and there's no pressure to be seen. So what we're going to have to do is we're going to have to use the gas law to exchange these two temperature functions with their equivalent pressure functions in the gas law. So what we'll get is, this is going to be step 7, what we'll get is P2V2 over R over P1V1 over R is equal to V1 over V2. I'm going to take that exponent right there and split it. This is a nice time. You'll remember a little bit about addition and multiplication of exponents. V1 over V2. And we'll make this one to the power of minus 1. All right, in step 8, we are going to take this left-hand side, which is kind of messy, cancel out the r's, and multiply by V1 over V2. So here's what we're going to get. We will get P2 over P1. And that will be equal to, and I'm going to show this to you so that the math is not an issue. We're going to multiply through by V1 over V2. And what we're going to multiply is this stuff up here, which I am simply going to rewrite. So that's going to be P1 over V2 to the gamma, and then V1 over V2 to the minus 1. And you can see that this will cancel and this will cancel. And that is going to leave me with V1 over V2 to the gamma, which once again I'm going to rewrite to be V1 to the gamma over V2 to the gamma. I didn't write this quite as well as I might have liked to, but let me see if I can straighten it up right here. In step 9, we're simply going to cross multiply the terms in step 8. So we'll have P2 times V2. So here we go. P2 times V2 to the gamma is going to be equal to P1 times V1 to the gamma. That is to say, every point on a PV diagram will multiply to the same constant. In other words, let's see if we can do this again. We're going to have PV to the gamma is equal to some constant. And that means that if we simply rearrange this, P is going to be equal to this constant over V to the gamma, and we remember that gamma is Cp over Cv. Finding this constant is really very easy. We can use any two known points. We can use our initial point P0 and our initial volume V0, and we know gamma, and so K will equal that. Okay, now for the afterthought. We're going to integrate this boxed equation up here in order to find work. So work is going to be equal to the negative of the integral from V initial to V final of the constant K over V to the gamma, where K is equal to pressure initial times volume initial raised to the power of gamma. Now, to do this, we're going to have minus K as the integral from V initial to V final. I'm going to rewrite this as V to the minus gamma. That puts it in a form where almost everybody can recognize the integral. So it'll be minus K over V final to the power of 1 minus gamma over 1 minus gamma. And then we will have minus a minus, which is going to be a plus K to the power of V initial to the 1 minus gamma over 1 minus gamma. Now, a lot of people would be perfectly happy with that, and there's nothing wrong with it, and that is a good final equation for work. This is equal to work. However, a lot of people also do a little bit more algebra, and I won't explain the algebra. You're going to have to figure that out for yourself. But it results in this formula, which is literally just simple algebra to get here. And this becomes V final to the gamma times gamma minus 1 minus K, and this one's going to be V initial over V initial to the gamma minus 1. So that explains how that is done, and we'll move on. Here I've shown an adiabatic curve graft. It's the blue curve in this graph, and the V initial and V final. Here's where V initial is. Here's where V final is. You can see they're both points on the blue curve. These other two curves that you see here are a couple of isotherms, not adiabatic curves, but isothermal curves. And the ISO 1 is set to go through V initial and ISO 2 is set to go through V final, and they're just here for comparison to the adiabatic curve. The pink or colored area under the curve is the work function, so that's the integral under the curve, and you can see that here the work function has been calculated out, and we're looking at 143 joules under these conditions. This particular one has also been set up so that the temperature can be adjusted right here, and in addition we can adjust V final and V initial. Now as it's set up right this second, V initial is at 0.5 liters and the final volume is at 0.1 liters, and so that's going to be a compression. In other words, we're going to squeeze the volume down. That's going to lead to positive work, and that's going to lead to an increase in temperature. Now I'll try to change these, and we'll bring V initial up, and we'll bring V final down. And then we will have an expansion work. In other words, V initial starts here at 0.08 liters and V final is 0.45 liters. So we now have an expansion, and that's going to cause negative work, and that's going to cause a decrease in the temperature. This widget, or graph if you will, is located at geogebra.com, and I have left a link to it down below. Thank you for watching.